momento. Hello, welcome. This is the first of the seminar series, and so the first speaker will be me. Okay, and the next talk will be in 2 weeks, because next week there will be the CDM in Rio de Janeiro, which is an event that has many talks, including talks in this particular days, so like Friday in the afternoon, and the group theory session, and so on. So, okay, so for this week I will be the speaker, and so let me share the screen. Okay, I will write. Okay, so I don't like to use slides very much. I hope everybody is seeing my screen. And okay, so yes. Okay, so the title of my talk is Primary Coverings. Of solvable and symmetric groups. So I don't know, maybe I can do this. And this is a joint work with Fumagalli of the University of Firenze in Italy. And okay, so first I want to start with the motivation. So the one motivation is given by pairwise generating sets. So if X is a subset of a group G, then we say that X pairwise generates G, pairwise generates G if for every pair of elements, so for every X and Y in X, X different from Y. And so note that, so this is like, okay, so there is a very interesting invariant, which is usually called omega of G, which is the maximal size of a pairwise generating set. And set for G. And now, how to study such a number? So, an interesting observation is that now I think I should do this. Sorry, I mean, I'm just having troubles here to remove this hide video panel. No? Okay, so maybe I'll do, I'll have to do it manually. So I need to do it manually because I am having trouble with, it's like a real blackboard now. Okay, so what was I saying? That that if you have two elements that generate G, then it cannot happen that both of them are inside any proper subgroup of G. So there is no H proper subgroup of G such that I mean simultaneously. I mean. So what I mean actually, so let me write it better, is that the set XY cannot be contained in A. Okay. So like, and this is where covering problems come in. Covering problems. So H is a family of proper subgroups of G. Proper subgroups of G. And H is a cover for G if the union of all the H in H is equal to G. And note that, so this implies that every X in X belongs to, remember that X was our pairwise generating set, belongs to precisely one. Precisely one member of H. No, I mean, I'm sorry. This is not what I wanted to say. So what I'm saying, so it's the opposite. What I want to say is that every H contains at most one. Okay, so every H contains at most one element of X because it cannot contain two because of what I said. So now this gives an interesting inequality that that is the following: that now if you have, so usually you define sigma of G to be the smallest size of a cover of G, and so cover meaning a family of proper subgroups whose union is G, and the basic inequality that you get is that omega of G is at most sigma of G, and this is because of what I said essentially. So we have an interesting inequality which also already allows to study this number. This is the largest omega of G is the largest size of a pairwise generating set. And so you see that this kind of covering problems have to do with generation. And the second motivation is that we can define another interesting invariant, which is the following. Nu, let's call it nu of G, which is the smallest number of proper subgroups subgroups of G so like say H1 HK, such that the GCD of all the indices is 1. So the index, so they have coprime index. Okay, so which is also an interesting number to study. And so usually in my talk G is finite, so you can easily see that we have a basic inequality, which is that the number of prime factors of the order of G, and this is because, so essentially, for every Silo subgroup, I can find, no, I mean, actually just choose H1, so you choose these H1 up to HK to be Silo subgroups. And of course, for distinct primes, and of course, the indices are coprime globally. So now, okay, now think. So now I'll move to the next. And now, so what is the connection of covering problems with this nu? So we define now gamma 0 of G. This was studied by Francesco Fumagalli, and this is the smallest number of subgroups H1 up to HK, such that every primary element of G, now I will tell you what is a primary element, belongs to a conjugate of some HI. So, okay, so primary means that element of order a prime power. Now, usually these are called P elements, but I don't want to use the letter P because it looks like P is fixed, so P is not fixed. So primary element is an element of prime power order. And okay, so and then we have a basic inequality, which is that gamma 0 of G is at most nu of G. And this is because, so if you have subgroups of coprime indices, then any primary element must belong to a conjugate of one of them, because otherwise, the prime defining this primary element would divide all of the indices. So what I'm saying is that if you have H1, HK that have global coprime index, then and you take the primary element G, so and G is primary, then let's say that the prime is P, so let's call the prime P, then find an I with P not dividing the index, and then inside HI there is a Silo. So this is a P Silo, and of course G does not belong necessarily to HI, but it belongs to a conjugate. So P to some, so let's say P to some X, which is contained in a conjugate. So, and this is a different type of covering problem. So because you see, we have conjugation here. And essentially, Francesco studied these two numbers, gamma 0 and nu. And in particular, he proved that if you have a group, if G is a simple group of degree n in case it's alternating, or rank n in case it's of Lie type, then I'm still talking about some motivation. Then nu of G, you can be bounded by a linear function of the number of prime factors of n, which is, so he proved some interesting results about these numbers. So what we decided to do, okay, is to drop the conjugation part. We dropped the conjugation part. So essentially, we considered the problems that I talked about, and we did so. So okay, let me explain because it's easier. So we define this. You do note that it's similar to sigma, but there is a 0 there, sigma 0. This is the smallest number of proper subgroups of G, which cover all the primary elements. Okay. And again, this is related, as I said, to okay, so to this somehow to this nu of G, because it has to do with gamma 0 that I just defined, where the conjugacy was taken into account, and it is also related to generation. So groups that can be generated by two primary elements in this case. So it is interesting. For example, you can define omega 0. I don't even think that it has been studied before, which would be the largest size of a pairwise generating set consisting of primary elements. And of course, sigma of G and omega of G, on the other hand, they have been studied a lot. So there is a lot of literature about sigma and omega. On the other hand, there is not much about this sigma 0. And it's interesting to ask, like, how can it be computed? So we want to cover primary elements, so elements of prime power order. And so, okay, so if so this makes sense if G is not a cyclic of P, so cyclic of prime power order. Because of course, I mean, if it's cyclic of prime power order, then there exists the generator cannot be in any proper subgroup. And an example, I don't know if to call it example, but so if so I will, when I consider sigma 0, usually I assume that it's not cyclic of prime power order. If or maybe I would say that in this case I would define sigma 0 of G to be infinity. This is usually what we do, in the sense that the needed number does not exist, but it's a notation that makes sense. So if G modulo the derived subgroup is not a P group, then sigma 0 of G is 2. And this is very easy to see, because you find inside G dash, inside the commutator subgroup, you find two subgroups of coprime indices. I don't understand. I mean, so I was saying that sigma 0 of G is 2 if G modulo G prime is not a P group, because if you take H and K of coprime indices then essentially you can work inside the derived, I mean the abelianization, and every primary element is either in H or in K. So and this is simply by using a little bit of silo theory and so on. And okay, so now let me continue. Now another couple of very easy things is that sigma 0 of G is always at most sigma of G, which is the same thing, but instead of covering only primary elements, we cover everything. And sigma of G is always, and also sigma 0, I mean, I'm sorry, sigma 0, like there are some properties that sigma has that it's always at most sigma 0 of a quotient of G. And this is easy to see. Now, what the first result that we proved with Francesco is that this is in like a 2021. With Francesco Fumagalli and myself, if G is solvable, G modulo G prime not a P group, then sigma 0 of G is 2. Otherwise, and this I already showed you, otherwise sigma 0 of G is equal to sigma of G. Okay, so essentially, if G modulo G prime is not a P group, then we have this by the reason that I told you. You choose two subgroups containing G prime that have coprime indices, and you see that there is a connection with this nu of G that I told you. And otherwise, essentially the number is equal to sigma of G. And by the way, in this case, sigma of G is it was computed by Tomkinson. Here Q is the smallest size of a chief factor of G with more than one complement. And okay, so now let me just tell you quickly what is a chief factor. So essentially, in this case, we know everything essentially about this number. And okay, so so either sigma 0 of G is equal to sigma of G when G is solvable, and in this case, it is 1 plus the size of the smallest chief factor with more than one complement, right? Or if G modulo G prime is not a P group, then sigma 0 is 2. So this is the minimal size of H modulo, the size of H modulo K, where
Vamos escrever a Martina que vem ver.
Não, ele só apresenta coisas.
Peraí que eu tô.
Norai pode se mudar. Peraí. Minimal normal subgroup of G modulo K. So essentially, a chief factor is a minimal normal subgroup. So this notation like means minimal normal subgroup of a quotient. So and H modulo K has more than one complement, more than one complement in G modulo K. Okay, a complement in a group is something. So what I mean is that inside the quotient, H modulo K has a complement. So it's like something like this, T modulo K. So it's a semi-direct product. This means what? This is what having a complement means. And so to prove this, I mean, we use some techniques that are quite technical. Okay, so essentially, probably I will not go into details, but let's say that maybe I will tell you one idea. One idea is that assume that so one idea is the following: assume that n in a particular case. Assume that n is a semi-direct product like this, where n is a minimal normal subgroup in G. Okay, and M is a maximal subgroup of G, and okay, and okay, N is abelian. Okay, abelian, and assume that sigma 0 of G is strictly less than sigma 0 of the quotient. If the quotient in this case is isomorphic to N, so sigma 0 of N. So assume that we are in this situation. So we have this strict inequality here. And in this case, there is a very nice argument which says that M and its conjugates belong to every primary covering of G, and the proof is interesting.
Algo positivo, né, nessa primeira possibilidade, então vai ficar só x também, né, por causa da definição do módulo. Essa aqui vai ser a primeira.
Como? Tá bom. Wait a second. So so the reason is that if so, let's say that let's call G0 the number of the set of primary elements. Primary elements. So let's say that G0 is contained in a union of subgroups. Then you can intersect it with M essentially. So M0. So you look at the primary elements of N. This will be contained in H1 intersection M, HK intersection N, and now this would be so let's say this would contradict this strict inequality. So here K is exactly the sigma 0 of G. So if you remember, so this inclusion will contradict the fact that we have the strict inequality here, if not for the fact that so since sigma 0 of G is strictly less than sigma 0 of N, M0 cannot be covered by K proper subgroups of N. So essentially this means that there exists one of the I's such that HI intersection M must be equal to N. I mean, cannot be a proper subgroup of N. Okay, so this implies that M is contained in HI, but now remember that M is a maximal subgroup, so M must be equal to some HI. So essentially, this gives you this idea, gives you gives you that there are many. So if you take a primary covering, there are many subgroups there, because you have n, this maximal one, and also all the conjugates of n. And usually the number of conjugates, it depends. See, in such a situation, it is at least, I mean, it could be that m is normal in G. Okay, this is one case, but if it's not, then it will have the number of conjugates is the order of n, and n represents, and either m is normal, or it has the order of G conjugates, order of n conjugates in G. Okay, and so all of them are inside the primary covering, and this exactly represents the chief factor. See, remember I said the chief factor with more than one complement. This is exactly this case, that you have exactly, you have a chief factor with more than one complement. In this case, because I just said that there are many conjugates. All the conjugates will be complements of n. So this is one idea that is used to prove such a result. And of course, I mean, it's much more technical, but I just want to tell you some ideas. And then let me move to the second result that we have in the paper, which is that which is the following. Let's call it theorem 2. Again, this is by Fumagalli and myself. And so let n be at least 3. Then we essentially asked what is the sigma 0 of symmetric groups. So sigma 0 of S3 is 4, and the sigma 0 of S6 is 7, okay? And then, of course, I mean, these are some small cases. So if n is a power of 2, larger than 2, then sigma 0 of Sn is 1 plus 1/2 n choose n over 2. And 3, if n is not of the form 3 to the epsilon times 2 to the a, where epsilon is in 0, 1, and a is larger than 1, then sigma 0 of Sn is 1 plus n choose n2, where n2 is the 2 part of n, 2 part of n. Okay, so the 2 part of n is the largest power of 2 dividing n. And 4, that I will not write because it's a bit more technical. We have some bounds. We have some bounds when n is 3 to the epsilon times 2 to the a, where, I'm sorry, 3 times 2 to the a, because this case essentially is a bit problematic. This is what I'm saying. That we essentially managed to compute sigma 0 of symmetric groups, except for this particular case here, which is a bit problematic. And of course, I mean, there are cases where we can do it, like 6, but in general, it's more complicated. Okay, so okay, this is a result that says that we computed the sigma 0 of the symmetric group in most cases. Okay, there is one exception, but we have some bounds. I would like to concentrate in particular on this, because I want to give you again some idea of how this is proved. I want to concentrate on this case when n is not a power of 2, and also is not of the form 3 times 2 to the a. So how to so let's say that first of all, you see that this 2 appears everywhere, like in all the cases. If n is a power of 2, if n is not a power of 2, so there is something special about 2. And yes, there is something special about 2 because this is very easy, that you can observe that the alternating group contains all the p elements, all the primary elements associated to odd primes. So if G has order p to the n, where p is an odd prime, then G belongs to the alternating group. See, because G will be a product of cycles of prime power, p power length, so they will all be even cycles. I mean, all these cycles will belong to An, so G will belong to An. So okay, use An because it's a good idea to use it. So essentially, what I'm saying is that probably this tells you that An will belong to primary coverings. I mean, it is useful to use An in your primary coverings. And actually, there is an argument that proves that if you want a minimal primary covering, that then you must use An essentially. So and then you can concentrate on so without loss of generality, the prime is 2. So you can concentrate on primary elements that have order a power of 2. Okay, so this is why the prime 2 appears more. So now you consider your set, and this has precisely n choose and 2 subsets of size n2. Okay, I mean, this is trivial even if it was not n2, but I'm saying that we use these subsets of size n2, which is the 2 part. And essentially, this implies that sigma 0 is at most 1 plus n choose n2. Because use, this one corresponds to An and what? And the stabilizers of X with X of size n2. X a subset of omega of size n2. So essentially, I'm claiming that if you take this and all of them, then you are covering all the primary elements. And the reason is that, I mean, it's funny that the reason, what I'm actually saying, like if you can reformulate what I'm saying in the following way, which is a completely unrelated to group theory, that it's so essentially this is a purely combinatorial statement. And essentially, what I'm saying is that if n is a sum of, so let's say that n is a sum of powers of 2. Okay, if you write n, let's say that if you write n as a sum of powers of 2, powers of 2, then there is a subsum which equals n2. And okay, so because okay, so first of all, this is a statement that you can prove. I mean, this is independent of everything. And it's interesting that it essentially proves what I was saying. What I'm saying is that if you take an element that has order a power of 2, then of course the cyclic structure of this element will be something like this. Any element of order power of 2 will have this cyclic structure, cycle structure, and then n is the sum of all of these powers of 2, and then we want to find a subsum which is n2 in such a way that we can find the set of size n2 with G belonging to the stabilizer of this set. And what will be this set? A will be the union of all the supports of the cycles that whose sum is n2, what I was saying before. So essentially this proves, what I was saying is that this proves that sigma 0 of Sn is at most 1 plus n choose n2, okay? Because you use the alternating group and you use the stabilizers of sets of size n2. And so the last thing to clarify a bit is what about the lower bound? Because you see that here we proved the upper bound, but I'm claiming that actually they are equal. So how to prove the lower bound? This is much more interesting in some sense and also much more complicated. So how to prove some lower bound in these particular situations? There is a general idea that that can be used, and this is the main problem. Let's say that lower bounds. Let's say that usually when you define something to be the minimal, for example, in the case of sigma, or the maximal number, in the case of generating sets, the maximal pairwise generating set, and so on, usually one bound is kind of easier, but the other bound is, so for example, in this case, the upper bound is reasonable, but the lower bound is much more complicated. So, okay, so now much more complicated. So find pi, which is a set of primary. So the technique is to find the pi, which is a set of primary elements that is hard to cover. And or if you want, I mean, this would be like in the terms of generating sets, this would be a set that is possibly pairwise generating set, or if it's not, then it's close to being pairwise generating set. So like you can all the time, you can always draw similarities between the two contexts. I just want to tell you about this because, like, to give you a motivation that I talked to you about in the beginning about these kind of problems that has to do with generation of groups. And now, so what will be the set? Okay, maybe I mean this will be a set that if you write, first of all you have to write n in base 2. So you write n in base 2. Where A1 is strictly larger than A2, strictly larger. So you can write n in base 2, okay? And then you define a set pi that looks like this. Just to tell you how it looks like, this set pi: 2 to the A1, 2 to the A2, 2 to the AT. Or in this case, this is when if n is not congruent to T mod 2. And then you need to define it a little bit differently if n is congruent to 1 modulo. So here we have 2 to the A2, a little bit different if n is at T modulo 2, okay? And essentially this will be a set that that is hard to cover. And what is the idea? The idea is that now you can even forget about it. I mean, you just have to remember that it's a set of primary elements associated to the prime 2. And then the lower bounds come from a nice idea of, I mean, we applied a nice idea of Marotti that is the following. It's okay. So so let's say that you have some family of subgroups, okay, H1, Hn. Hi is a proper subgroup of Sn, and this is called definitely unbeatable on pi, which is a subset of Sn. Remember, it's in this case it's a set of primary elements. If you have the following conditions, pi is contained in H1 union Hn, and B is that if you, so this is a covering condition. If you do the intersection of two of them, it will have empty intersection with pi for every I different from j. This is a partition condition. This is a kind of a partition condition. And C, which is maybe the most important, which is that if you intersect M with pi, and the size of it will be at most Hi intersection pi for every I, and for every M subgroup of Sn that does not belong to H, okay? So the third condition is the most critical. So essentially it says that if you have any other subgroup then that is not in the family, then it covers less elements than any subgroup in the family. And it covers less elements of pi compared to every subgroup in the family H. And then if this happens, then the minimal. So then, what is the minimal number of subgroups covering pi is exactly the size of H. So this is exactly how you prove lower bounds. So and you see the difference with covering all the primary elements is that in this case you can choose your set pi in a way that you can construct this family H. So essentially, it gives you a way to construct things and to prove some inequalities or some properties, and then deduce that. Okay, so to conclude here, that if pi is a set of primary elements contained in G0, then you have a lower bound for sigma 0. Okay, so I mean it's not hard to show that. So essentially, it comes directly from these three properties. That it's like you have to play some games. You take and by the way, this is this notion was defined by Marotti, Attila Marotti. I believe it was 2005. And the nice thing about this is that, as I was saying, it's easy using these three properties. It's easy to prove that you cannot do. So essentially, you see that these three properties. First one says they cover pi. The second one says that they cover pi in such a way that in a partition-like way, so there are no common elements between of pi between two different subgroups. And the third condition says that every member of the family covers many points, many elements of pi. So this implies that you cannot do better than that to cover pi. So you find the set pi that I was talking about is that set that I defined in the previous slide. And then of course, what would be in this case, in our case, the family H will be exactly stabilizers of sets of size n2. Okay. And of course, okay, if you okay, because you can forget about primary elements about order. They are covered by AN and it's always there and so on. And now it's interesting. So let me just tell you to finish. I just want to tell you that in some small cases, this was not. In some small cases, this was not possible because. Of course, I mean, these are very strong properties, and for example, for S10, we needed to use linear optimization. So let me quickly tell you what this is about. So we take maximal subgroups of G, and pi, a set of primary elements, hard to cover. I mean, okay, in the case of S10, we took elements of cycle type 442, and then the minimal size of a family H, such that H is contained in M, and the union contains pi, is equal to the minimal number of things of the form sum M in M of Rm, where Rm is in 0, 1, and for every M in M, okay, so no, I'm sorry. Rm is in 0, 1 for every M, and the sum in M is in Mx of Rm is at least 1 for every x in pi, and so here Mx is the members of M containing x, and now what the idea here is that this Rm tells you whether the subgroup M is in the cover or not. 0 is not in the cover, 1 it is in the cover, and this condition says that the family covers pi. Okay, because for every x, the sum must be at least 1. So this can be solved using a linear optimization program, computer program, and it's interesting because I mean, this was maybe idea, or I think it was his idea of Eric Schwartz, and I believe it was his idea. In general, I mean, this is an idea that he used many times to compute such things. And it's interesting because even if the groups are large, like S10, it's a very large group. By using not very strong computers, this can be calculated, this minimal number. Okay, so I'm done for today, and sorry for the inconvenience. And if there are any questions, please ask me.
Hi. So I have a question.
Yes.
You mentioned the result that sigma 0 of G is less than sigma 0 of M, where G is a symmetric product of N by N.
Yes.
Yeah. So using that result, I mean, since you already have the result about the symmetric groups, so can you generalize? I mean, is it possible to generalize the result for the Reed product of a finite group by a symmetric group, or specifically for a cyclic group by a symmetric group?
Yes, I think so.
You looked at that result.
Wait a second. Yes, where was I talking about this?
Yeah,
here.
Yeah, the next slide. Yeah. Or probably this
or
one.
the previous slide. Yes. Yes, in this
Yeah,
case.
this one. Yeah.
And so you say that you want, okay, so let me go here maybe that you want to consider a Reed product like CM Reed product with SN.
Yeah, and since you know the result about SN.
Yeah, this is a nice problem, and yeah, I mean this inequality you can have all the time you have. I mean, this is always at most this. Now the problem is that it's not clear how to prove equality, because usually, as I was saying, this is an upper bound, and the hard part is to prove the lower bound. But by the way, also the other Reed product is more interesting. So if I had to, this should be doable. So I would say that this would be, for me, I think this would be easier to do than the other one, because here you can construct elements that look like permutations. So I mean, let's say that so what I'm saying is that you can construct elements x1, xm, sigma, xm, y, something like that, where x1, xm are elements of the set pi or something like that, and maybe this will be just a generator of the cyclic group or something. And then using this set, I mean, maybe you can prove the lower bound, because in this case, I mean, it's harder. You have, so SN, I mean, it appears only once, and it feels like I mean, the second problem would feel more easy.
Okay. Thank you.
Thank you. Yeah, any more questions? Okay, so
well,
thank you.
Wait. Can you hear me?
Yes, please.
No, I just wanted to make a side comment, not really a question, very short one. That about covers of the group, there is an old problem in profinite group theory, where the profinite group, where the open subgroup of a profinite group can be covered by conjugates of a subgroup of infinite index. And that is old open problem. So it is not related really to the talk, but it is related to the topic.
So the open subgroups are covered by subgroups of infinite index.
No, but well, it is formulated like this. Suppose we have a profinite group G, subgroup H of infinite index. Take all conjugates of this of H and take a union. The question whether it contains an open subgroup. The question whether it can contain an open subgroup. Yeah. So the question is proof or disproof that it can happen.
Okay. So the union of the conjugates of H, right? The union of the conjugates of H. If the question is if it contains an open subgroup of G. Okay.
Yeah. Yeah. Assuming that H is of infinite index.
Okay. H is of infinite index. Yeah. Ah, okay. So it's more like if it can contain a subgroup of finite index.
Yeah, or whether the set can be open.
Mm-hmm.
That's a different approach, which is the same.
Oh. Thank you. Any more questions? Okay. So maybe I will stop the recording